Okay, Assalamualaikum and good day. Okay, we meet again in this third lecture. So we continue with the assembly programming. Uh, okay, as you know that any 16-bit non-segment register could have been used to perform the action below. Okay, if you look here, move CX. Okay, and then we have the immediate data 16-bit. So it means that you load the number 34E into a CX register. And then you can use the additional instruction. Currently, the value of CX is 34E. Okay, after you execute the move instruction, and then when you add CX with the immediate data, after you execute the instruction, so CX become C9F3. Okay, so the general purpose register, okay, as we have before, CAX, BX, CX, DX, okay, are typically used in the arithmetic operation. Okay, you know that register AX sometimes is referred as a accumulator. Later on in the more instruction which relate to the arithmetic, going to be used the AX register. Okay, now we go at the segment, program segment. Okay, basically, okay, the assembly language program consists of at least it has 3 segments. Okay, the first one is a code segment, okay, which contains the assembly language instruction that perform the task that the program was designed to accomplish. And the next one, we can have a data segment. Okay, normally data segment used to store information or data which need to be processed by the instruction in the code segment. Okay, and then we have the stack segment. Okay, and this stack segment is used by the CPU to store temporary information. Okay, these are all the uh, segment that we use in the 8086, which each of them actually they have their own register. Okay, a segment is an area of memory that includes up to 64K bytes. Okay, each of the segment it has a location, a space of 64K bytes, and begins on address evenly divisible by 16. Okay, so it means that the address will end in 0 hex. If you look back, I'm not sure either because we have changed the structure of the course. Last time we have teach 8085. Nowadays, you are start with the 8051. 8051 is a microcontroller. So 8085 is a microprocessor which address a maximum of 64K of physical memory. Means that it has a 16 pins for address line. So total, if you have 16 pin lines, you can have 64K location. You can address to 64K location. So in this limitation was carried out into 8086 design, which As you know that in 8085, everything put in that particular location. Okay, either the code, the data, the stack, all within that 64K byte of location. But in 8086, where there can be up to 64K byte for each of the category. Okay, we can have a code segment for 64K bytes, and we have data, and then stack segment. Okay, that is the new architecture, the improvement that they made after 8085. Okay, where in the literature concerning 8086, there are three types of address mentioned frequently. Okay, this being used by the one that study about 8086, how we can address, how we can define. Okay, the first one is the physical address. Since the 8086 it has 12 bit of this, 12 bit of address line. So actually on the address pin of 86, so it can have a range. The address can have a range between 00005 digit of hex number from all 0 to all F. Okay, physical, the actual physical location in RAM, either RAM or ROM. So it is within 1 meg byte of memory range. You can have 1 meg since you have 20 bit of address line. And then we can have, okay, is also being seldom being used is the offset address, where it is a location in a 64K byte segment range, which can range, okay, in the minimum one with four digit of hex number from all 0 to all F. This is what we call the offset address. And then we also have a logical address. Logical address actually which consists of a segment value. So the logical address actually you go to the segment register. Okay, that value is the logical address, and you combine it with a colon of the offset. Okay, the offset address. So logical address is the combination of the segment register value and offset address. Offset address. This is what we call a logical address. Okay, to execute a program, 8086 will fetch the instruction, okay, the codes, operand from the code segment. Okay, we go look at the code segment. Okay, this is where the instruction will be. Okay, and how you calculate the code segment, the physical address. Okay, so the logical address of instruction always consists of a code segment. Okay, we know that code segment is one of the register, and also the instruction pointer. This is the offset. Okay, instruction pointer. Okay, the combination of this, which being shown as CS double dot colon IP. Okay, this is the logical address format, where a physical address of the location, the actual address, we want to calculate, since you know that the 8086 you can have 20 bit of address line. So this 20 bit will show the physical address. And how you calculate physical address? Okay, physical address of the location of the instruction is generated by shifting the CS code segment register left by one hex digit, and then you add with the instruction pointer, the offset. Okay, now this is IP is the instruction pointer. We also know that instruction pointer also is another register, which actually instruction pointer contains the offset address as we discussed previously. So when you make this combination, when you shifting code segment left by one hex digit, then you add with instruction pointer, then you can have a total of 20-bit address, where this is where what we call physical address, since it put on the external physical address bus pin. You use this or to put on the address bus in order to access the instruction. Okay, let's look at the example. Assume that the CS, the code segment, and instruction pointer as shown in the diagram below. Okay. This is the format of logical address. You have the 4-digit of or 16-bit or code segment. Then you have colon, and then you have the instruction pointer, another 16-digit. Okay, which we call it as a instruction pointer. This is a register, and this is also a register. So the offset address contained in instruction pointer. The format of logical address, where the 16-bit digit after the colon is a offset. So in here, the offset, the IP is 95F3 hex. So the logical address, okay, this is the format CS colon IP. So we can put it as CS is 2500, okay, 2500. Then we have the IP. Okay, this is the logical address. So the physical address, as we looked before this, is the shifting of the code segment by one digit. So you make 2500, and then you add another 0, and then you plus with the instruction pointer 9FF3. So this is the physical address to access this location, the logical address location. Okay, calculate the physical address of an instruction. Okay, we look at this example. The one that the previous example 2500, then you shift left a code segment by one hex, add 0, and then you plus with instruction pointer 9F, so you get a physical address. The microprocessor will retrieve the instruction from the memory location starting at 5FE. Okay, this is the location of physical address. Okay, since IP instruction pointer have a minimum value of 0 and maximum of all F for the 16-bit, then the logical address in a single value of logical address, for example 2500 until 25 with all F. This is the range for a single code segment. address. Okay, this means that the lowest value location for a single code segment, 25 code segment here, 2500 to 500. Okay, the lowest is with, if you plus with the offset or the instruction pointer all 0, so you can have 25,000, and the highest will be when you have 25,000 plus with all F, so you can get 34 FFF. Okay, so this is mean the range of logical address with a single number of what we call code segment. Okay, you can have the lowest one, the range, until the highest one. So if what happens if the desired instruction are located beyond these two limits? Okay? It is not within this minimum and maximum value. So you need to change the segment in order to access that instruction. Okay, we look at these examples. Okay, if the CS is 24F6 and the IP is 63.4A, show the logical address. Okay, the first one. This is the logical address format. You have the code segment, and then you have colon, and then you have the offset instruction pointer. Okay, and then logical address and offset address. Offset address, B is the instruction pointer, 634A. And then calculate the physical address. Physical address, you need to shift the code segment by one hex number. Sorry, see here, okay. And then you plus with the instruction pointer. Okay, this is the results. Okay, 2B to AE. Okay, what is the lower range of that logical address? So the lower range, you have the code segment shift left by one hex plus with all 0 for the offset. And also we can have the maximum where the number of code segment plus FFFF for all the offset. Okay. So the next code segment, CS and the IP hold the logical address of the instruction to be executed. Okay. CS code segment and IP instruction pointer, okay, is the value of logical address where the instruction to be executed. Okay, the following assembly language instruction have been assembled, translate into a machine code and store in the memory. Where there are 3 columns, show the first one is a logical address, second one is a machine code at that particular address, and the last column is the assembly language code. The physical address is put on the address bus by the CPU to be decoded by the memory circuitry. Okay. This is the example. The first one is a logical address. Okay, this is the format of logical address. You have a code segment, colon, and instruction pointer. Okay, this is the address. The second column is the machine language or opcode and operand. Okay, and the last column is the assembly language. So if you look here, okay, if you look here, B057, since each of the memory location is 8-bit a byte, so if you have the machine language 2 byte, so you require 2 location. Okay, this is 1132.0.100. So the next machine language will be put is at 1132.0.102. Okay, it requires 2 location. Okay, instruction move AL57 has a machine code of B057, where B0 is the opcode and 57 is the operand. Okay, if you arrange it in each of the address line, each of the memory location, okay, if you look here, the logical address, this is the physical address. Okay, you know how to convert the logical address to the physical address. So B0 will be at 11420 physical address. 57, the next code will be at 11421, and so on. Of all the machine code will be placed to the memory location. Okay, as you know that instruction move AL57 has a machine code of B057, so it required 2 byte, where B0 is the opcode and 57 is the operand. The byte at the address 1132.0.100 contains value of B0, the opcode for a moving a value of register L, where the address of 1132.0.101 will contain the operand to be moved to the AL. Okay, the operand is 57. Okay, assume a program to add 5 bytes of data such as, okay, this is the value, 25 hex, 12 hex, 15 hex, 1F hex, and 2B hex. Okay, one way to add the item is as follows. Okay, you move the first value is 0 because you want to add it. So make sure that uh, currently the value of AL is 0. Then you add with the first value 25. And so on until the last value 22 hex. Okay, in the program above, the data and the code are mixed together in the instruction. Here, if you look, the instruction move add will be mixed with the value, okay, 25, 0, and so on. From this arose the idea of an area of memory strictly for data. Here, what we can do, you can put only data in particular memories, memory segment. Okay, where in the 8086, the area of memory set aside for a data, we call it as a data segment. Okay, the data segment use register DS. That's why we have DS, data segment. Okay, okay, debug and see, actually this is the compiler. Okay, some of the compiler require you to put hash. Some of it like debug you don't need because all of the number, all of the data is considered as a hex number. Okay, otherwise, you need to put the suffix hash, which refer to hex number. If you don't put it, will consider as binary, or you put B. Sorry, if you didn't put any suffix, it's considered as decimal, is 10, and if you put B, it's will consider the binary. Okay, we are going to look at the examples of the program to show how the data can be stored in the data segment. And the program written so that it can be used for any set of data. This is the advantage of using data segment, which you don't need to change any of the program if you require to change the data. If the in the previous example, if you need to change the data, then you need to rewrite all over again the instruction. Okay, you assume the data segment offset is 200 hex. The data is placed in the memory location as below. It as a data segment value, okay, which we can have it in the data segment register. This is the value which we use the same as in the previous examples. So the program, you can rewrite back the program as below. Okay, so you write AL in the beginning, you clear the value in AL, and then you add AL with the in bracket, you put it 200, so means the content of the logical address of data segment with the offset of 200 and put it to AL. And you can change, I mean, you can carry on with the rest of the instruction. So the offset address, which includes in the bracket, indicate that the operand represent the address of the data and not the data itself. You don't put, okay, this is means the inside the bracket. So this is the offset address for the data segment. If you didn't put the bracket, okay, you just put move AL, then the CPU will consider that 200 is the value itself, the data is going to be put in the AL. Instead of the content which the offset address is 200. So 200 here refer to a decimal number since you didn't put any suffix. Okay, this program will run with any set of data. Changing the data has no effect to the code, no effect on the code. So you don't need to change the code, only change the data. If the data had to be stored in a different offset address, and the program would have to be rewritten. Means that if you are going to access a different location for the address, okay, a way to solve it is by use a register which hold the offset address. Okay, and before each add increment the register to the next location, to the next byte. Wherein at 8086 allow the use of the register BX, SI, and DI, okay, source index and destination index, as an offset address for a data segment. Okay, the term pointer is often used for a register which hold an offset address. Okay, this is how you can write. Okay, but you need to initialize the offset register. Here, for example, the first one is to clear the value, clear the AL register, and then you put a value 200, which is the location that you are going to use to access the data, into a BX, and then you add it with the BX where you put in bracket. So it's not the value, actually it is a location that being pointed by BX. And then you can increment the BX value and access the next location, and so on. Where BX actually is used as a pointer. It's not a value, it's a pointer. The increment instruction actually is going to add one to its operand. In this example is BX. So BX will add with 1. Okay, actually this is the same results. Okay, if you later on, if you are going to study in detail, these two instruction, even though achieve the same results, but there are disadvantage of using one, because you require more space, and also is going to execute more machine cycle compared to the other one. That one is more in advance when you are if you are going, if you like to study in advance of the basic. If the offset address where the data is located is changed, okay, so only one instruction need to be modified. Okay, you only change the first instruction. Okay, you change the 200 to other location. The rest of the instruction no need to change. Okay, that is the the advantage of using the pointer rather than you write down the value itself. Okay, the physical address of a data is calculated using the same rule as the code segment. Actually, it's the same for the data segment as well. The physical address of the data is calculated by shifting the uh, data segment register left by 1 hex digit, and then you add with the offset value. So, okay, this is the example. Okay, this is the value of the data segment register. You shift it 1 by 1 hex. Okay, means that you put 0, and then you add with the offset value. Okay, we look at this example. If DS is 7FA2 hex and the offset is 4388E, then calculate the physical address at the lower range and upper range of the data segment. Okay, the first one is the physical address. B is the lower range, okay, where you have with all zero offset, and then this is upper range when you add with all F. Okay, this is a logical address of the data. Okay, look at the one example of 1.4. Assume that DS register is 55, 57, 8C to access a given byte of a data at a physical memory location 67F66. Does the segment, okay, this segment, cover the range where the data reside? This is the range of the data. This is the physical address location of the data. Does the data segment cover this value, cover the range where the data resides? If not, what change need to be made? Okay, if you look here, if you have this data segment register value, so if you add with all F for the offset, this is the address. Until this address is the highest location that you can access, and this highest location actually is not within this memory location. So the location of 6L is not included in this range. So you need to change DS in order to access the physical memory location of 67F double. Okay, in the previous example, we use the 8-bit or 1 byte data. Okay, so what happens if you are going to use a 16-bit data? Okay, for example, here, move AX, 3FF3 hex. You want to load it into the AX register, and then you want to move it to the location of data segment where the offset is 1500s. So copy the content of AX to the offset of 1500s. So the lower bytes of the low memory location and high byte goes to the high memory location. Okay. If you look here, F3 is the low byte and 35 is the high byte. So F3 will put into DS 1500, where 35, the higher byte, is going to be put at the S 1501, where this is, we call it as a little endian and big endian, okay, versus big endian. So currently this is the little endian, where in the big endian method, the higher byte goes to the low address. In the little endian method, the high byte goes to the high address and the low byte go to the low. Okay, there are a different. In certain processor, the what we call the endian is being fixed by the manufacturer. But in certain processor, you can choose either you want to use the little endian or big endian. Okay, let's look at the example 4.5. Assume the location with the following contain DS6826, which is 48, and the next one is 22. Okay, show the content of the register BX. If the instruction move BX, okay, move BX with the offset 68, 37, 26, sorry. Since a BX is a 16-bit number, so it's going to take 2 bytes. So according to the little endian conversion, which used in all 86 processor, register BL. Okay, in BX we can have either BL or BH. So BL should contain the value from the low offset address. Okay, so 6836, and the BH, the value from the offset address 6827. The next, the high address. So in here, BL will be 48 and BH will be 22. So this is the little endian convention. Okay, in all Intel microprocessor and many microcontroller, they use the little endian convention. Where Freescale, where formerly is a Motorola microprocessor, along with some other microcontroller, it use the big endian. Okay, it's not the same. Okay, now we have go through the uh, code segment, data segment. Now we look at the extra segment. Okay, this is another segment which available in the 86. Okay, in ES, which we call it as extra segment register, use an extra data segment. Where in many normal programs, this segment is not used. You don't use it uh, formally. Okay, where it used in essential for a string operation. Okay, in where in extra segment 20-bit address of 8086 allow to access 1 megabyte or 1024 kbytes of the memory space with the address range from all 5 digit of hex until all f of the address, where during the design phase of the first IBM PC, engineers had to decide on allocation of a 1 megabyte memory space to a various section on the PC. Okay, this memory allocation, we call it as a memory map. This is the example of how we map the memory. For example, you allocate RAM for 640K, so it will range from all 0 to 9F. The other 4 digit is F hex, and then we allocate a video display RAM, which is 120K, okay, from A on 0 and so on. Okay, and ROM another 256. Okay, of this 1 megabyte, this is the range we set aside for the RAM, and then 130K for video memory, and then we have other remaining 256 for ROM. Okay, when in the early 80s, where most PC come with 64K or 256K bytes of RAM, were more than adequate at that particular time. Okay, where user had to buy memory to expand up to 240K. This is during the early stage of design of PC. Okay, managing RAM is left to the window. Okay, because the amount of memory used by window actually varies. Different computer have a different amount of RAM. Where memory needs of application package, where is varied. Okay, for this reason, we do not assign any value for the DS, CS, DS, and SS register. Where that assignment actually means that specifying the exact physical range from 0 all to 9F, and this is beyond the knowledge of the user. Okay, it's set by the operating system. Okay, from A or 0 to BF is set to a video where the amount used and the location vary depending on the video board installed on the PC. And C0 all to F all is set for the ROM. Not all the memory in the range is used by the PC ROM, even though you have the space, but not uh, uh, everything is installed in that space. Actually, ROM is the one that being being installed for being used. It is a read-only memory, means that you don't change the instruction or the data inside the ROM. Okay, 64K byte location are used for BIOS. BIOS is ROM. Okay, basic input output system. Some of the remaining space is used by various adapter card, for example, network card and so on. The 640K bytes from 0 to this is for RAM, referred to as a conventional memory, where 384 kilobyte from this address are called the UMB, upper memory block. Okay, some part of it we are not going to discuss it in detail. Okay, uh, it's just the exposure of how the computer system being developed. Okay, I will stop here and we are going to continue for the next lecture.